Welcome to the deep dive. Today we're looking at something really foundational, the way we design and construct our buildings.
Yeah, it's fascinating stuff.
We've got a great collection of information here, all centered around sustainable architectural design.
Right. Think of it as kind of a blueprint for building today, but in a way that respects, future generations.
Finding that sweet spot
Right.
between our needs and what the planet can actually support.
Exactly. And the core idea, as our material lays out, it's meeting our current needs
Uh-huh.
without compromising the ability of those who come after us to meet theirs.
Which immediately brings up that tension
Mm.
between what we demand and the Earth's, finite capacity.
Absolutely, is a critical point.
And this overview we're looking at, it gives us a really useful kind of a three-part framework for how to approach this.
It does, makes it clearer.
First, it's about smart initial choices, thinking about local culture, aesthetics.
And really leveraging the natural benefits of a site, right? Like sunlight and wind.
Yeah, exactly. Then second, it's about intelligently using energy that's just there, freely available.
Right. Looking at everything from how the building is positioned to the materials it's made of, even the air quality inside, how we handle water, waste.
And that definitely connects strongly to the thinking behind LED. You mentioned that earlier.
Yeah, leadership in energy and environmental design. It's a big framework for this stuff. The second part really emphasizes using those available resources by looking hard at the site.
Uh-huh.
The building envelope, there's like the skin, walls, windows, roof, foundation.
Got it.
The materials we pick,
Yeah.
indoor air quality, water management, minimizing waste. It's all interconnected.
And the third part?
That focuses on reducing our dependence on fossil fuels,
Yeah.
using the most efficient technical systems we can.
Okay. So our goal today is really to dig into this overview, pull out the key ideas, the practical insights
Yeah, the actionable stuff.
that can help anyone really grasp how to create buildings that are just, well, more sustainable.
Okay, let's unpack this, starting with passive sustainable design. Sounds interesting.
Oh, passive technologies are great. They essentially work with nature,
Right.
taking advantage of natural energy flows, minimizing fossil fuel use. But to make them work well,
Yeah.
you really need a good grasp of material properties, heat transfer, and definitely the local climate. That's essential.
Absolutely. And one of the most basic but crucial things is just the site itself, isn't it? And how the building's oriented.
Totally fundamental.
Our source reminds us, the Earth's tilt gives us seasons.
Mm-hmm.
And knowing the sun's path is key for stuff like passive solar heating.
And what's cool is how simple some solutions are. The source talks about finding south with just a stick and its shadow.
Oh, yeah. How did that work?
You mark the shadow tip, wait a bit, mark it again. Draw a line bisecting the angle between those points in the stick. Bam, north-south line.
Wow. Low tech, but effective. Exactly. This basic understanding of orientation is like the cornerstone. Maximize sun in winter, minimize it in summer.
It really shows sometimes the best solutions aren't complicated. And speaking of working with the land, building into a slope, advantages there too.
Definitely. It's like using the Earth as natural insulation.
Keeps it warmer in winter, cooler in summer.
Pretty much. You're using the Earth's thermal mass to create a more stable temperature inside. Less need for mechanical heating and cooling.
Right. Now, capturing solar energy, it's not just about letting sun stream in, is it? The source talks about storing that heat.
Yeah, that's where high thermal mass materials come in. Masonry, stone, concrete, adobe, even water.
Like thermal batteries.
Exactly like thermal batteries. They soak up the solar heat coming through south-facing windows. And then, as it gets cooler outside, they slowly release that stored heat back into the room. Keeps things comfortable.
And then there are trum walls. I found that concept really interesting. Can you walk us through those?
Sure. A troop wall is basically a big, heavy wall, often concrete or masonry, right behind a south-facing glass wall.
Okay.
Sun comes through the glass, heats the wall surface. That heat then slowly moves through the wall and radiates into the room.
And the source mentioned vented and unvented versions.
Right. Key difference.
So what is it, and when would you use each?
Okay, so a vented system has openings, top and bottom. The air trapped between the glass and wall heats up, rises, and flows into the room through the top vent. Gives you quicker warmth.
But maybe stores less heat in the wall itself.
Exactly. An unvented system, no vents. It maximizes heat storage in the wall mass, releasing it more gradually.
So unvented might be better if you need heat mainly at night.
Generally, yeah.
Yeah.
Or in more moderate climates.
Yeah.
Vented might be better in colder places needing daytime heat. It's about matching the system to the need.
Makes total sense. Tailoring it.
Yeah.
The source also briefly mentioned calculating efficiency guidelines using a conservation factor, CF and R values. Quick recap.
Sure. CF is basically a multiplier for estimating energy use in simpler calculations. R value, that's thermal resistance.
How well something resists heat flow.
Yep. Higher R value, better insulation. Designers use these to figure out how much insulation is needed to hit energy targets, meet codes, that sort of thing.
Got it. Okay, moving on. Keeping cool naturally. Ventilation. The source mentions atria, those big open central halls. How do they help cool things down?
It's simple physics, really. Hot air rises, right?
Less dense.
So an atrium with openings at the top may be exposed to prevailing winds. The rising hot air gets carried away.
Creates a pressure difference.
Exactly. Draws cooler, fresh air and at lower levels. It's a really elegant passive cooling method.
Like the building's breathing. And there are other strategies mentioned, operable windows, ventilation towers. What's key to making those work well?
Placement. Absolutely crucial. Exhaust points need to be high up to catch that rising hot air.
And intakes.
Positioned to catch the prevailing winds. Often on the opposite side. The source actually gives a great real-world example, the Queen's Building Auditorium at De Montfort University in the UK.
Oh yeah, that was cool. Remind us how that system works.
Okay, so fresh air comes in through concrete ducts under the seats.
Under the seats. Clever.
Yeah. Then, as the air warms up from people and lights, it rises naturally and gets expelled through two big chimney stacks behind the stage. They can even control the airflow with louvers. It's a system built on understanding air movement. Works really well.
Amazing to see those basic principles applied so effectively. Okay, let's shift gears. Tapping into the Earth's own energy. Geothermal. The source talks about it on two scales, right?
That's right. Large-scale electricity generation and then passive ground source heating and cooling for individual buildings.
So the big scale, power plants.
Yeah, typically they pump water deep down to hot reservoirs or rocks. Water gets superheated, comes back up, turns to steam, drives turbines, generates electricity. Then they often re-inject the water.
Okay. And the passive side. That seems more directly relevant for homes, smaller buildings.
Right. Passive ground source uses what are called closed-loop ground-coupled heat pumps, or GCHPs.
GCHPs, got it.
They use the fact that a few feet down, the Earth stays at a pretty constant temperature, maybe 50, 60 degrees Fahrenheit year-round.
Stable.
Very stable. So in winter, the ground's warmer than the air. The heat pump pulls that warmth out and puts it in the building.
And summer.
Opposite. Pulls heat out of the building and dumps it into the cooler ground. It uses a vapor compression cycle and buried pipes, the heat exchanger, to do this transfer.
So the ground's like a heat source in winter and a heat sink in summer?
Exactly. The source also mentions earth tubes, another passive technique.
Earth tubes? What are those?
Another smart way to use that stable ground temp. You bury a series of tubes,
Okay.
draw outside air through them. As the air travels, it gets preheated in winter or pre-cooled in summer before it even hits your ventilation system.
Reduces the load on the main system.
Significantly, yeah. Especially where you have big temperature swings.
Ingenious. Okay, back above ground. Solar hot water and wind power. Increasingly important.
Yeah, for hot water, flat plate collectors are pretty common. Dark absorber plate, transparent cover, fluid to carry the heat, insulation.
Standard setup.
Pretty much.
Yeah.
And you need an expansion valve for safety. The source notes optimal tilt is usually latitude plus or minus 15 degrees facing true south.
Makes sense. And wind. We're definitely seeing more turbines.
For sure. Capacity is growing fast globally, even if it's still a smaller slice of the pie overall. And the source mentions hybrid systems too, wind and solar combined.
With batteries.
Often, yeah. Especially good for off-grid places. Gives you more consistent power, day or night, sun or no sun, wind or no wind.
Makes a lot of sense for remote spots. Now, turning waste into energy?
Biomass.
Right. Biomass is just organic matter used as fuel. The source highlights microturbines.
Well scale.
Yeah, like 1.5 to 20 kilowatts. They can run on various gases, even methane from landfills or digesters.
And generate electricity and heat. Yep, right on site. Offers some resilience against fuel price swings, and it's a more sustainable way to handle certain wastes.
So power generation and waste management. Smart. Let's zoom out again, site design. It's not just the building itself, right? The whole space matters.
Totally. The source stresses planning open spaces and buildings together from the start.
Integrated approach.
Yeah. Let's plan for water, reuse gray water for irrigation, rainwater harvesting, and using plants strategically for shade. That can cool the immediate area by like 10 to 15 degrees Fahrenheit. significant local cooling.
Wow, that's a big difference. And that helps fight the urban heat island effect the source mentioned.
Absolutely. Urban heat island, that's cities being noticeably hotter than surrounding rural areas.
Why does that happen?
Mostly because buildings and pavement absorb and hold more heat than natural landscapes, plus waste heat from cars, AC units, all that stuff.
How much hotter can it get?
The source says maybe 6 or 7 degrees Fahrenheit difference, which impacts energy use, health.
Right. The source had that great example, the ING Bank in Amsterdam. Their landscape design.
Yeah, really efficient. Their gardens are watered entirely by harvested rainwater. Saves money, obviously.
Sure.
But they also reported a drop in employee absenteeism. Suggests a greener workplace has wider benefits, maybe.
Interesting connection. Multiple benefits stacking up. And Village Homes in Davis, California. Another example of community planning.
Yeah, designed ecologically. Narrower streets encourages greenery, pedestrian-friendly, plus community gardens, good solar access for most homes, shows how community-level design matters.
Okay, digging deeper into that thermal impact, it's not just buildings causing the heat island.
You know, those impervious surfaces, roads, parking lots, they soak up heat too, and when rain hits those hot surfaces...
Heats up the runoff water?
Exactly. That warm runoff flows into rivers, lakes,
Yeah.
can raise their temperature, harm aquatic life.
A ripple effect we don't always think about, but roof gardens, green roofs, they help mitigate this.
Big time, like the one on the Commerzbank Tower in Frankfurt. The plants cool through evapotranspiration.
Uh-huh.
The roof surface radiates less heat, they absorb some pollution, and they manage stormwater by soaking up rain. They cool the building, cool the area around it.
Living skins for buildings, basically. Multiple wins. Now,
Yeah.
climate responsive design. Sounds like one size fits all definitely doesn't apply here.
No way. Building orientation, for instance, has to respond to the local climate. Maximize the good stuff, minimize the bad.
Examples.
Phoenix Central Library, hot, dry climate, lots of shading, special glazing to cut heat gain. Buildings in hot, humid climates, they need overhangs, maybe elongated shapes for cross-ventilation, open plans for airflow.
Working with the climate, not against it, and considering neighbors, too, their impact on sun and wind.
Crucial. How buildings are clustered affects the microclimate around each one, their long-term energy use. It's not always thought about enough in planning. The source mentions creative shading, like Le Corbusier used in India, and how effective cross-ventilation is, especially in humid places. Sometimes boosted by stack ventilation, letting warm air rise and exit high up.
Smart strategies. What about the solar envelope? Sounds intriguing.
It's a zoning concept, basically, a theoretical 3D space around a building site,
Okay.
defined to make sure neighbors still get adequate sunlight access. The shape depends on the site, latitude, time of year. It's a planning tool to promote solar access for everyone.
Like fair share rules for sunlight in a community? Cool. And historical examples. Cliff dwellings, monasteries. What can we learn?
Those often show a deep understanding of local conditions built up over generations.
Right.
Cliff dwellings use the rock's thermal mass, natural overhangs for shade. Buddhist monasteries in India often clustered to catch wind for ventilation, built into slopes.
Wisdom from the past.
Definitely. The source also notes that reusing existing buildings, clustering new development that's sustainable too, fights sprawl, reduces need for new infrastructure.
Saves embodied energy, less disruption.
Exactly. And finally, on this climate stuff, the idea of sense of place, respecting the site's topography, not just flattening everything.
Yeah, working with the land's character.
Right. The site's natural form creates microclimates, gives it identity. Shouldn't just bulldoze that for convenience, the source argues. There's a connection between people and land to respect.
Very important point. Okay, let's move inside. The building envelope. The barrier between inside and out. Huge role in sustainability.
Absolutely fundamental. Walls, windows, roof. The foundation controls heat flow, noise, weather protection, impacts air quality, and the energy savings potential.
Yeah.
Up to 50%, potentially, just from envelope improvements like better insulation, ceiling leaks.
Wow, 50%. So the goal is managing heat transfer, keep heat out in summer, keep it in during winter. You mentioned R value and U value earlier. Remind us.
Sure. R value is resistance to heat flow. Higher R is better insulation.
Okay.
U value is the rate of heat transfer, how much heat gets through. Lower U is better insulation. Your inverses.
Got it. So understanding those is key for an efficient envelope. And heat moves in different ways, right? Conduction, convection, radiation.
Precisely. Conduction is direct contact. Convection is fluid movement, like air. Radiation is electromagnetic waves. Need to understand how these work through building materials in both summer and winter.
And infiltration, air leaks. Big deal.
Huge deal for energy loss. Cold air leaking in during winter, hot air in summer, puts a big load on your HVAC.
Right.
The source gives Q values quantifying leakage rates for different cracks, openings, even small leaks add up. Sealing them is just as vital as insulating well.
Two sides of the same coin, insulate and seal. The source mentioned calculating heating needs, net load coefficient, NLC. What's that about?
NLC basically estimates the total heat a building is expected to lose over 24 hours, factoring in envelope losses and internal gains from people, lights, etc.
Why calculate that?
Crucial for sizing the heating system correctly. Don't want it too big or too small. Also helps estimate total heating energy used for the season.
Okay, makes sense. Let's dive into insulation itself. Lots of types mentioned: loose fill, foam boards. What are the main kinds?
Yeah, several options. Loose fill like cellulose, fiberglass, mineral wool, often uses recycled stuff. Good for tricky spaces.
Uh-huh.
Sprayed foam expands, creates a tight air seal, high R value per inch. Foam boards are rigid, offer insulation and sometimes structure.
What about radiant barriers?
Good at blocking downward heat flow, useful in hot climates like under roofs. Then you have SFPs, structural insulated panels, prefabricated sandwich panels.
And straw bale.
Yep. Surprisingly good thermal resistance because the walls are so thick.
Sounds like there's an option for pretty much any situation. The source referenced EPA recommendations for insulation levels. Good guidelines to follow.
Generally, yes.
Mm-hmm.
EPA gives recommended R values based on climate zone and fuel type. Good starting point for efficiency and comfort. The source also stresses things like manufacturer certification, proper vapor barriers with certain foams to avoid moisture issues.
And retrofitting insulation in existing buildings. More complex.
Yeah, be trickier, yeah. Access can be limited,
Yeah.
but often it's one of the most cost-effective energy upgrades you can do.
Worth the effort then.
Definitely. The source shows typical spots, attics, walls, crawl spaces. Just needs careful planning to do it right. Avoid trapping moisture.
Okay. Now, materials. That story about the oak beams at New College, Oxford. Really thought-provoking. What's the lesson there?
It's amazing, right? Long-term thinking. Centuries ago, they planted oaks, knowing they'd need them eventually to replace beams. It's about life cycle thinking, planning for the future, a real culture of sustainability.
Puts our typical short-term view in perspective. The source emphasizes the 4 R's: reduce, reuse, recycle, rejuvenate.
Yeah, those should guide decisions throughout the whole process. Design, material choice, construction waste, end of life, everything.
And construction and demolition waste. It's a massive amount, isn't it?
It really is. Source says a typical house build creates maybe 2.5 tons of waste, demolition, 20 tons or more. Most ends up in landfill.
Wow.
So a key goal is cutting that way down. Smarter procurement, designing to minimize offcuts.
Which brings us to embodied energy. What does that include? Why track it?
Embodied energy is the total energy used across a material's entire life cycle.
From start to finish?
Yep. Raw material extraction, processing, manufacturing, transport, construction, all of it. The source distinguishes initial embodied energy to build it and recurring maintenance, replacement, usually measured in megajoules per kilogram.
So choosing lower embodied energy materials reduces the building's overall environmental hit.
Exactly. It's not just about operational energy, but the energy baked into the materials themselves.
And the USGBC, for LEED, encourages reusing buildings and materials and using renewable or certified stuff.
That's right. Reusing buildings and materials is often the most sustainable choice, avoids all the energy needed for new stuff. After that, using rapidly renewable materials or wood certified by FSC Forest Stewardship Council, that's next best. The LEED rewards those strategies.
Okay, specific materials. Engineered lumber. How is that more sustainable than solid wood sometimes?
Engineered wood products like LVL, OSB, some plywoods often use smaller pieces, waste wood, or faster-growing trees more efficiently.
Gets more usable material from the resource.
Pretty much. Things like engineered trusses, I-joists, T-joists,
Yeah.
they make better use of the wood fiber.
What about steel and cement? Big energy users, right? More sustainable options.
Well, for steel, using recycled content is huge. The source mentions Rush University Medical Center in Chicago, 90% recycled steel in the structure.
Impressive.
They also use other recycled products, FSC wood. For cement, yeah, production is energy intensive, but using recycled aggregates in concrete, optimizing the mix design, researching alternative cements, those help reduce the impact.
So even with conventional materials, choices like recycled content matter. Okay, windows and glazing, critical for light, but also for thermal performance.
Absolutely critical. The source mentions California's Title 24 standards limiting window area setting maximum U factors, heat loss, maximum solar heat gain.
There are rules to push efficiency.
Yeah,
Yeah.
and specific limits on west-facing windows in homes because they get so much afternoon sun.
We talked U factor. What about solar heat gain coefficient, SHGC?
SHGC measures how much solar radiation gets through the window and turns into heat inside.
So you generally want low U factor and low SHGC.
Usually, yeah. Especially in warmer climates or for windows getting a lot of sun.
Wow.
Lower U means better insulation. Lower SHGC means less unwanted heat gain. The exact targets can depend on frame material, skylight mounting too.
The light to solar gain ratio, LSG, sounds useful for comparing windows.
It is. LSG is visible light transmittance divided by SHGC.
So,
A higher LSG means the window lets in a good amount of visible light without letting in excessive solar heat. It's efficient, gives you daylight without jacking up cooling costs.
a good balancing metric. And better frames help too. Insulated vinyl hybrid frames.
Definitely. Insulated vinyl frames have internal chambers, often filled with insulation, much better than standard vinyl or aluminum. Hybrid frames combine materials maybe wood inside, durable vinyl or aluminum outside, with thermal breaks to stop heat transfer.
And intelligent building facades. Sounds futuristic.
Getting there, these are dynamic systems. They can actually respond to the environment. Adjust shades, change glazing transparency, optimizing comfort and energy use automatically.
Wow, the building adapting in real time. Cool. Let's move to floors and roofs. Key considerations there.
For floors, especially ground contact ones, need good, rigid insulation underneath, and moisture protection is vital.
To prevent dampness, heat loss.
Right. For both floors and roofs, timber or steel, enough insulation is key for energy savings and how they connect to the walls. That joint is critical for stopping heat leaks, air leaks.
Makes sense. And cool roofs. We hear about those a lot. Why are they sustainable?
Simple idea. They reflect more sunlight, absorb less heat than dark roofs.
So the building stays cooler?
Yep. Reduces AC demand, saves energy, makes non-air conditioned spaces more comfortable, can even make the roof last longer by reducing temperature stress.
How do you get a cool roof?
Different ways. Reflective coatings on various materials, membranes, shingles, metal, or using inherently reflective materials.
Smart, especially in hot places. Now, daylighting using natural light. The source mentions daylight factor, DF.
DF measures indoor light level as a percentage of the unobstructed outdoor light level on an overcast day. Quantifies how well daylight is getting in.
So you can estimate it.
Yeah, the source gives a simple way based on window area, room size. Uses library and workshop examples to show target DFs and how to estimate the actual average DF, considering north and south windows, room depth.
Helps designers figure out how much window area they need for light without overdoing it. But outside obstructions matter too, right? Overhangs, other buildings.
Absolutely. They can significantly cut down how much light actually gets inside. A good daylighting design accounts for all that maximize the benefits, minimize glare or unwanted heat.
Okay, but we still need electric lights sometimes. The source says designers need to understand lighting power, equipment, basics.
Yeah, understanding voltage, current, power in watts. A lighting system has parts. The lamp itself, maybe ballast to control power, a reflector to direct light, a lens or diffuser, and controls like switches or dimmers.
And lamp types. Lots of options now.
Many. Fluorescent, CFLs, metal halide, sodium vapor, tungsten halogen, and of course LEDs. Big differences in efficiency, lifespan, use cases. Incandescents are pretty much obsolete now, energy-wise.
LEDs have really changed the game. The source also mentions software for lighting design and standards.
Yeah, programs like Radiance, AGI-32
Yeah.
let designers simulate lighting in 3D, optimize for light levels and energy use, and following standards from UL, CBM, NEMA, ensure safety and performance.
Got it. Okay, HVAC, heating, ventilation, air conditioning, often the biggest energy hogs.
Can be, yeah. They handle temperature, humidity, ventilation, air movement, filtration.
Yeah.
But a well-insulated, passively designed building might need much less HVAC energy to begin with. That's key.
Reduce the load first.
Exactly. The source lists cooling system types, small units, central AC, heat pumps, evaporative coolers, even solar or waste heat-driven chillers for big applications, and different ways to distribute the air.
Evaporative coolers, swamp coolers. Good in dry climates. How do they work?
They pull air through wet pads. Water evaporates, absorbs heat from the air, cooling it down. Uses way less energy than AC in dry air. Not great in humid places, though, and needs water.
And right-sizing HVAC is crucial, based on the reduced load from good design.
Absolutely. Oversized systems waste energy, cycle inefficiently. Need to match the equipment to the actual lower demand you've achieved through passive design and good insulation.
Makes sense. General strategies for efficient HVAC.
Maximize passive systems first. Choose high-efficiency equipment when you need mechanical. Use smart controls. Also consider occupant density for ventilation needs. Use good filters for air quality. And manage moisture carefully to prevent mold.
Which leads right into indoor air quality, IAQ. Poor ventilation can make indoor pollution worse.
Definitely. Indoor air can collect pollutants from materials off-gassing, furnishings, cleaning stuff, people, plus outdoor pollution coming in.
Right.
If ventilation isn't good enough, those pollutants build up. Can affect health, comfort. Source advises checking for things like radon, mold, CO, asbestos, depending on the situation.
So sustainable design isn't just energy, it's health too. EPA and LE have guidelines. Focus on source control.
Yeah, choosing low VOC materials, paints, carpets, furniture that's source control. Plus, ensuring proper ventilation rates dilutes and removes pollutants. Good IAQ doesn't have to mean compromising design.
Okay, vital resource, water. Efficient use is part of sustainability. How?
Uses less energy for treating and pumping water, so less fossil fuel use. Strategies include efficient fixtures, reusing gray water.
Water from sinks, showers, not toilets.
Right, use that for irrigation. Also, solar hot water systems save heating energy. And reducing stress on wastewater systems, rainwater harvesting, pervious surfaces, bioswales, living machines for on-site treatment.
Gray water recycling sounds smart. Benefits.
Reduces demand for fresh water, obviously. Lowers wastewater flows needing treatment. Can help recharge groundwater. And the nutrients can feed plants. It's a more closed-loop approach.
Makes sense. Lastly, in this section, sustainability audits and rating systems like Energy Star, LED.
Audits help assess existing buildings, find ways to improve energy performance. Energy Star rates commercial buildings top 25% energy performers get the label. Their Target Finder helps set goals for new projects.
And LED.
Offers different certification levels, certified, silver, gold, platinum, based on points earned across various sustainability categories. Green Globes is another system. They all help set benchmarks, drive better practices.
Good ways to measure progress. And the potential for CO2 reduction in buildings is huge.
Massive. The building sector can deliver really significant emissions cuts through better efficiency and sustainable practices.
Okay, to bring this all together, the source gives several case studies, real-world examples. Let's look at a few quickly. Clearview Elementary School. Key features.
Geothermal heat pumps, underfloor air system for better ventilation, central recycling space, and importantly, they chose materials based on life cycle analysis using software like Bees and Athena. Really holistic.
Thinking cradle to grave for materials, founding Farmer's Restaurant.
High recycling rate for construction waste, urban location near transit, window shading, maximized daylight, in-house water filtration, waterless urinals, low-flow fixtures, efficient dishwasher, used salvage wood, sustainability in the details.
Covering lots of bases. Hawaii Preparatory Academy sounds innovative.
Very. Experimental nighttime radiative cooling system using water on the roof stored underground, solar PV and wind turbines, battery backup, solar thermal for hot water, building monitoring system, bought carbon offsets, aiming for net zero water and energy for their science building.
Really pushing the envelope. Proximity Hotel.
High-performance insulated wall panels with recycled content, large operable windows for light and air, green roof for insulation and stormwater.
Nice combination. And Sokolblosser Winery. Sounds very site-specific.
Very. North orientation to reduce sun load. Used uninsulated concrete walls, leveraging the Earth's coolness. Natural ventilation with a heat stack. Earthen roof minimizes runoff. On-site, water reuse for irrigation, water-wise landscaping, very connected to the site.
These examples really show there's no single formula, is there?
Not at all. It's about picking the right mix of strategies for the building type, climate, site. But thousands of buildings show it's possible. Great design, affordability, function, and environmental responsibility.
Integrates form, function, delight, and responsibility.
Exactly. It comes back to that three-step approach. Think about site and climate first. Use free energy intelligently through design, then minimize fossil fuels with efficient systems.
So wrapping up this deep dive, it's clear sustainable architectural design offers this huge toolkit, really.
Yeah, from understanding site nuances to choosing materials and systems wisely.
It really empowers you, our listener, to think differently about buildings and how we can all contribute to a more, responsible future through how we build.
And maybe think about which of these ideas resonate most. Which could apply to your own home or work or future projects? What part sparked your curiosity today?
Definitely good questions to ponder. And if you want to dig deeper,
check your local building codes. Look for incentives for sustainable practices. And the websites for LED, Energy Star, Green Globes, tons of info there.
Great suggestions. Thanks for joining us for this insightful deep dive.